Same thing is true with chemicals. So a chemical reaction will reach an equilibrium, and that's when both the reactants and products are present in amounts or concentrations that will stay consistent with time. So a reaction can go very much to completion, very much toward products. It can kind of go half and half between reactants and products. It can really not go to products at all. It might just want to stay at reactants. And I've had reactions like that where you only get 20% of it to go, and you got to take what you can get. So the point is, in a chemical reaction, the reactants and the products will form in a certain ratio. And we usually say that equilibrium is reached when the forward reaction proceeds at the same rate as a reverse reaction. And we can affect that equilibrium by changing the conditions, just like we did with the cat. You could do that at lunch too. You could probably think of ways that you could clear off a table at lunch, bring in something that everyone is definitely not going to want to smell or whatever. All right. So let me escape this for a minute and get into, what did I want to show you now? Reverse and forward reactions. That's what I was going to show you. Excuse me. And that's here. Here it is. All right. So here we have a reaction. And when we let this go, the chemicals are forming iodine and hydrogen, or HI. And there's a point right when we start that one product is being formed more than the other or something. And then we have a situation where now the forward reaction, the reaction for I2 and H2 to run into each other and form HI, is happening at the same rate as the reaction of I2, HI and another HI splitting apart to form H2 and I2. So the forward reaction and the reverse reaction are happening at the same rate, and the concentrations of the two will stay the same. So let me just reset that and show you again. So here we have a certain 50-50 ratio, but as we start the reaction, some of it will go to product, and product will form, and then after a while, some of that product will go back to reactant, and then the reaction will have the same ratio, even though some stuff is coming back and some stuff is going forward. And I don't love this thing, but it was the best I could find. All right, so what does that have to do with anything? Let's talk about energy and reactions. So we did a reaction for you, the sudsy kinetics of the elephant toothpaste or whatever, where we took peroxide and we showed you that it can turn to water and oxygen. And in fact, the prevalence of this reaction is known from the fact that when you buy peroxide in the store, it's 3% peroxide. It comes in a brown bottle, and that's because light will make this reaction happen more frequently. Another thing that will happen as a result of this reaction is you form this gas. You form oxygen gas. So when you buy a high concentrated peroxide like we had to for that, you may remember it came in sort of an accordion or slinky looking can. And that's so that there was room to expand in case some oxygen formed. It wouldn't explode. It would actually just make the can get a little bit bigger, or the container get a little bit bigger. So anyway, that being said, so that's the reaction we're looking at, peroxide going to water and oxygen. And as you can see here, peroxide has more energy than water and oxygen, and that should be known to you since much of the planet is covered in water. It's a pretty stable compound. Not much of the planet is covered in peroxide. It's not as stable, so it's higher of energy, higher of potential energy. And any reaction is going to need some activation energy to make the product. So here we call that the difference in energy between our reactants, our peroxide, and what we call the activated complex, sort of this very top of the hill where it can go one way or the other for equilibrium purposes. But so here's our activated complex. The amount of energy it takes to get peroxide up there is called the activation energy, symbolized by EA. And once it reaches that activated complex, it can then go down the hill to water and oxygen. So if that energy to get to the activated complex is small, then it's going to be what we call a spontaneous reaction, which means it doesn't take much to make it happen. All right, so this is an example of an exothermic reaction. So the energy difference between the products and the reactants and the products is such that the products are of lower energy, so energy will be released. And we call the difference in energy between the reactants and products the enthalpy, and it's symbolized by delta H. It's a change in energy, basically, and it's delta H. But it's a change in the the energy between reactants and products. And in this case, it's 98 kilojoules per mole, I believe. I didn't write it down, but let's say that's what it is. So that means 98 kilojoules will be released because of the energy difference, the potential energy difference between this higher up peroxide and this lower down water and oxygen. So we have a negative sign in front of the energy because it's released, and the reactants lose that energy. They lose 98 kilojoules to become products. So exothermic reactions are when reactions release energy, and that would mean the reactants are of higher energy than the products. Now let's think about the reverse reaction here. So if we wanted to go from water and oxygen to this activated complex so that we could get over here to peroxide, what is our activation energy now? Is it going to be bigger or smaller than what it was? So this is what it was. But now to get to that activated complex, we need, hopefully, oops, you can see, we need more energy. So that's a bigger chunk of activation energy because it has to account for this difference in enthalpy plus the original activation energy of the forward reaction. So the activation energy for the reverse reaction is much larger. And that's going to be true for exothermic reactions. That's why they tend to stay at products, because it's harder for the products to go back to reactants because there's a much higher energy threshold it needs to reach the activated complex. So this is the same thing shown now where the products are at the beginning and the reactants from before. So now the reactants would be the water and oxygen, and we're trying to make the product of peroxide. But as you can see, the activation energy is higher. We're still trying to get to this activated complex up here. So here's our activated complex. And the relative energy now is such that the products are of higher energy than the reactants. We have to put energy in. So our delta H is the same number, but different in sign. Going the other way, it would be negative because it was going down. Now it has to go up. So it's a positive delta H. So the enthalpy is positive. It's an endothermic reaction. The products are higher energy than the reactants. Now, if we add a catalyst to a reaction, so if we look at that first reaction where peroxide, and we did this in class, peroxide's going to water and oxygen. If we add a catalyst and we use sodium iodide, I call it potassium, but basically we're using I minus, that reaction proceeds faster because we lowered the activation energy. And by lowering the activation energy, we made this reaction occur easier. The delta H did not change as a result of adding a catalyst, though. And the catalyst was just helping the reaction go faster. So you increase the reaction rate, but you do not change the enthalpy. If I can take a minute here, here's the picture of it, but I can actually show you on here because I have it up and running. So here is the situation where we have a high activation energy, right? Here are our starting material, and they want to get over here to products, and we have a high activation energy. So one way we can overcome that is by heating it up, give those things more energy so they can get over the hump. And so I'm going to heat them up. And as you can see here, some of those green A reactants want to get over. They just got to figure their way over there. And hopefully when I get one over, and there it goes. All right, so I got a B. So I got one B, and now I got two B. So this is happening, right? But it can happen a lot faster if there was a way for me by adding uh, a catalyst to reduce this activation energy by lowering that gate between them. Now there's easier distribution to happen to product, and that's what we saw in the sudsy kinetics or the elephant toothpaste reaction. Basically, we made it faster happen. So notice the product energy versus the reactant energy is not any different. We just made it easier for things to go back and forth. And as far as equilibrium goes, you can see here that things are going back and forth. We lowered that threshold so things can go back and forth. So if I freeze it here, we have a ratio of 14 reactants to 16 products. So that's sort of where the equilibrium is going to lie. So if I let it react a few more minutes and I hit the pause again here, sort of just when I'm, all right, so we have 13 reactants and 17 products. The ratio is staying pretty much the same as the point of our 30 particles. 13 or 14 will be reactants, and 16 to 17 will be products. All right, so, and as I mentioned, if raising the activation energy is going to sort of make it difficult for things to go back and forth. and we can help them go back and forth by giving them more energy to overcome that. And we'll talk about that in a minute. All right, so back to this. So other factors that can influence your reaction rate besides a catalyst, which will lower the activation energy, we can change the temperature, as you just saw, right? We can change the temperature of a reaction, and that can help things go from A to B and also back from B to A. We can change the concentration or the surface area. So let's get into a different simulation here. I'm not thrilled with this, but it's the best there is out there that I could find thus far. All right, so here we have chlorine gas, Cl2, and here we have sodium atoms. And for these things to react, if we get it going, they need to collide, right? The chlorine has to actually see the sodium so that it can make salt, sodium chloride. So there has to be a collision. Now, ways we can make these collisions occur more frequently is a couple things. We can increase the temperature, which unfortunately, even though that's a thing here, it won't let you move it, which is frustrating. But anyway, but you can imagine if I increase the speed of these molecules flying around, they would collide more often, and then reaction could occur more quickly. The reaction rate could occur more quickly in this case. Also, I can increase the concentration. So here's a situation where we have the HI molecule, hydrogen iodide, that's the H, that's the I, and we're going to form H2 and I2. So if we make this reaction occur, you can see they have to hit each other first for the hydrogen and the iodine to form. So let's hit a freeze here. So here's our H2 molecule, here's our I2 molecule. The HIs have to hit each other. So these two look like they're about to hit each other here, or maybe these two, I don't know which direction they're going in, but let's see. All right, so there you go. So once they hit each other, they can react, and we can influence the reaction rate by, again, increasing the temperature. And I think this one might let me do that. Let's try it. Let's reset it. And let's increase the temperature. Nope, I don't think it will, but let's try it anyway. Let's increase the temperature. Nope, but you can imagine if these are moving around faster, the collisions can occur and give them the energy to do what they need to do. The other thing we can do, if I reset this, is I can increase the concentration, right? By having more things in there in this volume, the same volume, but I have a higher concentration, a greater amount in that area, I have more collisions, right? And I can make that go a little faster because it's just more likely two things are going to hit each other. So getting back to this, so increasing temperature will increase collisions, or if you want to decrease the collisions, you want to decrease the temperature. Increasing the concentration would increase the collisions. If you want to decrease the collisions for your reaction to occur, you would decrease the concentration. Or surface area, you can expose more of the reactant. If you look at the sodium situation here, right, it's all down here at the bottom. It's kind of stacked on each other. If we spread those out so that they were all over the place, or there was more area for these chlorine molecules to hit, if it had more pockets in there for them to go into, we could increase the amount of collisions we need. So surface area is another thing we can use as a way to influence a reaction rate. So I'm going to stop it there. That's going to be the reaction rate talk, and I will talk about